Solve this linear motion problem. We got to get a graph of x versus t. Having read it, I can see that it starts out behind the start line, so we're going to have negative and positive values for x versus t. And then we'll need a v versus t. I don't know if this thing's ever backing up or yeah. Move forward, accelerate, move forward, come to a stop. So this is all going to be positive. So I'll put the origin down here at the bottom of the V line. And it looks like it breaks up into 10-second intervals. I'm going to just focus on these for a while, these two graphs. And let's have that be 10 seconds, and then 20 seconds, and 30 seconds. So 10 seconds. I think I'll put the units over here. 10 time in seconds, and so that's 20 and 30 seconds. 10, 20, and 30. Alright, let's see if I can, I like to start with a v versus t, that's usually the easy one. So, what do we got? Start moving forward at 20 meters per second. Gonna go up to 40 meters per second. And then it comes to rest. Okay, I think I got it. So I'll go 20 and 40. 40, and we need units for this, so be in meters per second there. So it starts out at 20, goes forward at a constant speed for 10 seconds, and then it accelerates at a constant acceleration, meaning v versus t is straight, for another 10 seconds, and then it slows down at a constant rate. These are all straight line segments. I'm not sure that one looks all that straight, so I'll go ahead and label them. This is straight and horizontal. And alright, I think that takes care of it for the velocity. Let's check that out. Moves forward at that speed for 10 seconds. Alright. I want to get like x values so I know what to set the scale. It starts out at minus say x0. I'll call this like t0 equals 1. This is t1. So this is 0 by the way, but t0, t1, t2, and t3. So x0 represents the position at time t0. So the subscript 0 corresponds to time t0, which is 0 seconds, minus 250 meters. And it's moving forward with a speed v0, which is 20 meters per second. Forward at that speed for 10 seconds. So x1 at 10 seconds is going to be equal to the delta t's are all 10 seconds. I think I'll write that down. Delta t equals 10 seconds. So x1 is going to be x1 0, well, x0 plus v0 times delta t, because this is constant. So x1 is minus 250 meters plus 20 meters per second times 10 seconds. That's 10 times 20, that's 200 x1. Looks like it's minus 50 meters. Alright. Then the car starts accelerating forward at a constant rate and does so for 10 seconds. Gets up to 40 meters per second. So let's say V2 at this time is 40 meters per second. That's given. And I want to find the acceleration from 1 to 2. I go V2 is equal to V1 plus the acceleration from 1 to 2 times delta t. It's always that 10 seconds. So V2 20. Oh no, I'm trying to get A12. So A12, subtract the V1 from both sides. I'm switching sides, so V2 minus V1 all divided by delta t. So that's 40 meters per second minus 20 meters per second all divided by 10 seconds. So that's 20 divided by 10. That's 2 meters per second squared, A12. So A0 to 1 is 0. And then A12 is 2 meters per second squared. And I think I'll use, to get x2, I'm going to actually use, it's x1 plus v0 plus v1 divided by 2 times delta t. So I was thinking of using the A12 for this, but I'll use that equation that doesn't involve that. x1 I found to be minus 50 meters. That was 20 meters per second plus 40 meters per second. Plus 40. That plus sign's not coming out too well. Plus 40 meters per second, all divided by 2, and then times 10 seconds. So x2 let's see, that's going to be 60 divided by 2 is 30. That's 300 minus 50 is 250 meters. It's meters per second up there times seconds, so it does come out in meters. That term does too. So I got x2 is 250. And then it's still going forward after that, and it's slowing down. I think I'll just take it, the area, I choose to do it a different way. Area under the curve from 10 to 20 to 30 seconds. x3, you could use a constant acceleration equation. I choose to use the area under the curve, area under, well, I should say it's x2 plus area under v versus t from 20 seconds to 30 seconds. That's 1/2 the base times the height. So it's x3 is equal to 250 meters So I guess I'm showing you how to show the work if you decide that you want to use the area under the curve method. Obviously we could use x3 is equal to v2 plus v3 all divided by 2 times delta t. But the area, the height of that thing is 40 meters per second. I think I'll write this down. This is 1/2 base times height. So I'll put the, oops. I'm going to use the eraser for this. I want to put the base in first, since I said it's 1/2 base times height. So it's plus 1/2. The base is 10 seconds. And the height is 40 meters per second. I'm looking at this triangle right here. And the height of it, 40 meters per second. The base of it, the width of the base is 10 seconds. So that's 200, so that gets us up to 450 meters. And so my graph, it goes from minus 150, no, minus 250 up to 450. So up to 450. If I call that 500, I go 1, 2, 3, 4, 500. Minus 500 is 500. I'm going to try 100 for that tick mark, and there's a 100 for a tick mark in here that's kind of hard to see because I had that 0 for the time axis. Alright, I think I can actually do that one now, but I'm gonna save it and did all that work to get ready to do it, and I want to do the acceleration versus time graph. This looks steeper here, so it's going to go more negative than it goes positive. A versus T, and what do we have? We had 2 in there. I haven't gotten the acceleration for the last part, so I'll go for that last segment. V3 is equal to V2 plus A on the interval from 2 to 3 times delta t. So A23 is V3 minus V2 divided by delta t, and that's equal to 0 minus 40 meters per second divided by 10 seconds. So it's equal to a minus 4 meters per second squared. Just calculating key values. So let's go ahead and get that. I'm going to go 2 minus 2 minus 4. This is meters per second squared, everything on this axis, so that's 2 minus 2 and 4. And then we're using the same time scale for all of them. So this is 10 seconds, 20, 30, it's 0. Then it jumps up to 2. And then it jumps all the way down to 4. If you want, you can put these vertical lines in. I don't care. Either way is fine. But we shouldn't be going past the 30-second mark there. So I got to erase that. And I got A versus T done. So now it's time to work on the X. Starts out at minus 250. I think I'll do that one in black too. So 1, 2, 3, 4, 5, 4, 3, and 250 is in there. Constant, and x1 is minus 50. So I got a straight line. I'm going to label that straight because I can't draw it all that straight. And then it speeds up. So it's got the same speed just before 10 seconds as it does just after 10 seconds. It starts speeding up gradually, so I'm going to have a smooth curve joining on there. But the slope is going to be increasing, and I got to get up to, where's x, to 250. So that's 100, 200, 250, getting up to there. So what a nice smooth curve. I'm going to put that on there as curved up. It looks so close to straight that somebody could think it was just my lack of drawing ability that makes it look like it's curved up. So I'm putting curved up on there. I'll put little notches in there so people know straight from here all the way to there, curved up from there to there. And then it gets to 450 is my recollection. And it's slowing down, so it's curved down from there to there. Actually comes to a stop, so it comes in horizontal at this point. And I don't think I've got it quite horizontal. Alright, I'm going to put horizontal right there in case it doesn't look like it's quite tangent to the horizontal, and curve down. Okay, notice how smoothly these join. Right there and right here. There's no kink at either location. So even though it's a little hard to tell that it's curved up there, looks like I did a little better with the curve down there. Of course, it's curved down more steeply to get flat at the end there. But notice it's got some positive slope here, and it's just got a little bit more positive slope here, although the slope went to 0 here. So that H doesn't look very much like an H, so I'm going to add a little bit to it there and doctor it up. So horizontal right there at the end, what I'm pointing to with that arrow. Alright, that should tell the reader anything the reader doesn't know. Label key values, that means label them on the graph. I'm going to do that in a different color. So started out at minus 250 meters. The times are all key values, but they're all labeled. At this point it's at minus 50 meters. I calculated all these things. I think that's x to 250, and then 450, 250, 450. So 250 meters. And 450 meters, if I remember that correctly. 250 and 450. Okay, I think the rest are going to be pretty easy. This was 20 meters per second all the way across. I'm really labeling that whole line. Got up to a maximum of 40 meters per second. 0 meters per second here. Alright, and then 2. So it looks like it's lined up pretty close with the 2, but just to follow the directions. And minus 4 meters per second squared. And I think I want to read, I'll go ahead and put 0 for this line. 0 meters per second squared for the acceleration. And I'll go ahead and read the question and make sure I got everything. Straight line forward. Minus 250 is where it starts. 20 meters per second. So I started moving forward. Should be at a positive I. Yep. Moves forward at that speed for 10 seconds. Starts accelerating forward at a constant rate. Gets up to 40. Starts slowing down. Does so for 10 seconds. And is at rest. Okay. Draw position versus time, velocity versus time, acceleration versus time from the start to the end. Label the key values. Okay, I think it's done. Let's call that a solution.